This chapter is about areas and volumes. If you have a shape on, say, a piece of paper, it encloses a space. Well, a closed shape encloses a space, because technically a line segment is a shape, but that doesn't enclose space, right? Okay, so a closed shape, like say a parallelogram or a rectangle, which is a type of parallelogram, or a trapezoid or a circle, these enclose an area. And if you have a three-dimensional shape, it encloses volume. Three-dimensional means it doesn't just have vertical axis and horizontal axis, it also has depth. So if you have a piece of paper, something you draw on the paper that has a vertical and a horizontal. But then, if you say fold that paper, which is flat, into a paper airplane, that paper airplane has length, width, and depth. So it has 3 dimensions. For now, we start with area of parallelograms. The area A of a parallelogram is a product of its base B and its height h. This is B, the base. And the height would be, well, it could be drawn anywhere, but often you see it drawn from one vertex to the opposite side. What do you mean opposite side? Technically, it's opposite sides, i.e. the sides that don't touch that vertex. Because I could say this is the base and that's the height. It just needs to be perpendicular to the base. So at 90 degrees, right angles. Okay, so that's the height. Let's do an example. Find the area of a parallelogram if the base is 6 inches and the height is 3.7 inches. Okay, so base, this is 6 inches. And the height is 3.7 inches. Okay. Well, we have area equals base times height. That's the formula for parallelograms, including, say, for rectangles or squares or rhombuses. So, 3.7 times 6, or 6 times 3.7 is equal to 6 times 7 is 42, so 2, and then we carry the 4. 3 times 6 is 18, 18 plus 4 is 22. 22.2 square inches, or inches squared. Okay, now let's find the area of this parallelogram. It's 12 centimeters by 8 centimeters. You know why the formula for a parallelogram's area is base times height? Well, let's say we cut this triangle out and we move it up here. Oh, hey, we now have a rectangle. And we know that a rectangle is just width times length, or length times width, depending on which you like to write first. Okay, so area is equal to base times height. So 12 times 8, which is equal to 96 square centimeters. Let's say we have a few other parallelograms. Oh, we got to round to the nearest tenth if necessary? That's not a problem. Why? Well, here we have whole number and 1 decimal place. Whole number, 1 decimal place. When we multiply, we will have at most 1 decimal place. And here we have whole numbers. Okay then. So, 13, we should state the formula first. Area equals base times height. 13.2 times 5, which is equal to, well, 2 times 5, we carry it over and it's a 1. 3 times 5 is 15. So added to the carried one, that's a 6. So it's 66. What are the units? Well, these were in feet, so it's foot squared, or square feet. Okay, now what about this one? Area is still base times height, which is 8 millimeters by 4.6 millimeters. And 6 by 8 is 48. 8 by 4 is 32. So it's 36.8. Another way we could have done this was, hey, 4.5 plus 0.01. Okay, 4.5 by 8 is the same as 9 by 4, which is 36. And then the 0.1 times 8, that's just 0.8. What are the units? It's millimeters squared. Okay. What about 16 inches here, height, and 17 inches base? Well, area is still base times height, which means 17 by 16. And 7 by 16 is 6 by 7 is 42. And 1 by 7 is 7. So that's 112 plus 160 gives you 272. We have triangles and trapezoids. The area A of a triangle is equal to half the product of its base B and its height H. A equals 1/2 base times height. Why is this? Well, let's say we have any triangle, okay? What happens if we have another identical triangle, but put it like that? We have a parallelogram. Any parallelogram can be cut into two identical triangles. Any two identical triangles can be made into a parallelogram. And a parallelogram's area formula is base times height. Therefore, the area of the triangle is 1/2 base times height. All right, what if we have a trapezoid? There's two ways you can make this formula here. One way is put the divide by 2 under the base 1 plus base 2 term, in which case you are drawing congruent triangles here and then turning this into a rectangle. You can think of it as flipping these triangles up. So that's one way. What's the other way? Well, the other way is that you draw a diagonal and cut this into two triangles. 1/2 height times the one base and 1/2 height times the other base. And you add them together and you factor out the 1/2 height. So, depending on preference and regional convention, you may write this slightly differently, like h over 2 times b1 plus b2, or just this whole thing over 2, or h times this part over 2. Those may indicate which method your region prefers, the rectangular method or the two triangles method for teaching trapezoid areas. But for our purposes, we're going to just go with the two triangles method because, hey, wait a second. Once you draw that line, it quickly becomes relatively apparent. You don't need I need the average of the top and bottom bases. You can just go, hey, this is a composite shape. It's just two triangles put together. Yeah. So let's find the area of a triangle with base 3 millimeters and height 5 millimeters. Okay, area is equal to 1/2 base times height. So 1/2 3 millimeters times 5 millimeters This is going to be 7.5 millimeters squared. Let's say we have a trapezoid with bases 5 centimeters and 1 centimeter and height 10 centimeters. So this is a pretty tall and narrow trapezoid. Okay. So this is area is equal to 1/2 height times base 1 plus base 2. So it's 1/2 times 10 centimeters times 5 plus 1, which means we're looking at 5 times 6 or 30 centimeters squared. Okay. Now, how about these figures here? Round to the nearest tenth if necessary. Well, okay. I don't think it will be. 7 feet and 12 feet. Well then, area is equal to 1/2 base times height, which means 1/2 base 12 feet times height, which is 7 feet. So, that's 42. And the units are not meaning of life, it's feet squared. Okay, 9 millimeters by 7 millimeters, but it's a triangle, so area is 1/2 base times height, which means 1/2 base 7, height 9 millimeters. So 7 by 9 is 63, so we're looking at 31.5 millimeters squared. Now for 3, let's space our things out a little bit. So this one we can, 4 we can do on this side. 3 we'll do here. Area is, this is a trapezoid, therefore it's going to be 1/2 times height times base 1 plus base 2. Or 1/2 height base 1 plus base 2, which is equal to 1/2 times 5 inches times base 1, 14, plus 7. So 1/2 times 5 times 21. How can we make this multiplication easier? Well, this is 5 times 10.5. Hurrah! Therefore, it's 52.5. What are the units? Oh, it's inches squared. Okay. Number 4. Area is, well, 1/2 height times the sum of the bases, or height times average of the bases. You'll notice that height times average of the bases is easier to say. But mathematically speaking, the two triangles method is actually easier to think of. Like if you need to rederive the formula at any point. How interesting. Perhaps this is why there are different methods of writing the trapezoid area formula. The area is 1/2 height times base 1 plus base 2. Okay, so that's equal to 1/2 of 13.5 times base 1, which is 18, plus base 2, which is 8. Okay. And, how can we make this multiplication relatively simple? 13.5 versus 26. We can go with 13 times 27. I mean, that's one way, but then we have the 1/2 over here. So really we're stuck with 13.5 times 13. So we're looking at, oh yeah, this sort of dashed line divider is a relatively good idea if you at any point start running into the wait a second, where are my equal signs close to problem. Also, if you need multiple columns on one page, I recommend dashed line dividers. Most of the time they're pretty obvious on what you're talking about, so teachers can just understand them directly. Of course, please do make sure that yours can. So 13 by 13 is 169. Okay. And the 0.5 by 13 is 6.5. Look, it's good to have a calculator. It's good to know how to use your calculator. Sure. But much of the time, on a lot of contests, for example, you aren't going to be allowed to use a calculator. Which means mental math. Lots and lots of mental math. So you should be aware of various tricks to break up numbers to make them easier to deal with, and so on, just for your convenience. So 175.5. Are we missing something? 175.5 what? Ants? Grasshoppers? Chickens? No. This area is centimeters by centimeters. So centimeters squared. Units are critically important in math and physics because if you got your units wrong, you have probably done something very, very no good. So, circles and circumferences. A circle is a set of points in a plane that are the same distance from a given point that we call the center. So the center for this circle would be here. And a diameter crosses from one side of the circle to the other through the center. A radius goes from the center to any point on the circle. So the circumference, C, is the distance around the circle. So C is on the outside. C equals 2 pi r, or pi d. Now d would be this distance is d, and this is r, radius. So let's find the circumference of a circle with diameter of 7.5 centimeters. Well, circumference is equal to pi d. So because pi is an irrational number, there's exact value is just going to be pi times whatever diameter is. It would just be 7.5 pi centimeters. This is exact values, okay? The problem is that this isn't very useful. Like, you go to a store and you tell somebody, oh, I need to buy 7.5 pi centimeters of string. What are you doing? Yeah, no. So that's why we have these things called approximations. And this would be approximately, if you round to the nearest tenths, i.e. the 0.1 digit, you end up, or one decimal place, you end up with 23.6 centimeters, approximately. Uh, let's say we have a radius instead of a diameter. And the radius is 14 inches. What is the circumference? Well, circumference is equal to 2 pi r. You can only, if you want, you can just really bother with only going pi d or 2 pi r, and then just remembering that r is 1/2 d, or d equals 2r. Like, you don't need to remember both c equals 2 pi r and c equals pi d formulas, even though eventually you inevitably will remember them. 2 pi times 14 inches is 28 pi inches. But you are not going to be shopping for any, I don't know, what sort of item would be 28 pi inches long? That's not very long. Huh. Well, anyway, it comes out to approximately 88.0 because it rounds up from 87.9645, etc. inches. 88 inches. Huh. Actually, yeah, that's like a casket length. But hey, this is talking about the circumference of a circle. Anyway, exercises. Find the circumference of each circle. Use 3.14 for pi. Round to the nearest tenth if necessary. Well, diameter equals 6 kilometers. Okay, c equals pi d. Which is going to be 6 pi kilometers. It said round to the nearest tenth if necessary. And given that we're dealing with pi's, yeah, it's going to be necessary. So 6 times pi is approximately 18.8 kilometers. Okay, depending on convention, you may have to put the units on the last exact value you have as well. But we're just going to skip that. Radius equals 23 miles. This is a big circle. C equals 2 pi r, so equals 2 pi times 23. That's 46 pi miles, which is approximately 3.14 times 46, because it says use 3.14 for pi, approximately 144.4. The units here are miles. Okay. So, diameter equals 6.3 meters. Well, we know that circumference is equal to pi d. Therefore, 6.3 pi, or approximately 6.3 times 3.14 meters. So 19.8 meters approximately. Let's say the diameter is 5 1/4 millimeters. Well, then it's still c equals pi d. Therefore, this is equal to 5 1/4 pi. 5 1/4 is 5.25 times 3.14. So 16.485. Yeah, that's approximately 16.5 millimeters. This, if you had rounded again, you would have ended up with 17, which would have been incorrect. That's why whenever you round, you should start with the last exact values you had. Otherwise, you end up with cascading rounding errors. And you should only round at the last step of each part of a problem. And if you need to use that number for the next part of a problem, use the last exact value you had. Area of circles. The area A of a circle is pi r squared. The square of the radius multiplied by pi is the area. So let's say we have an area with radius 5 centimeters. Equals pi r squared. We write out the formula and then we substitute. Pi and then times 5 squared. So we end up with 25 pi centimeters squared. Is this a useful number? Like say, you tell somebody, I want to buy a pizza that has a surface area of 25 pi square inches. Because 5 centimeters, that's not a pizza, that's a biscuit. Anyway, so is this very useful? No. Therefore, usually we have approximations. Conventions vary on how many digits to use by default. And I'm going to just use the pi button on the calculator instead of going 3.14, which is the most common approximation that you use at school if you're not using a calculator. So this is approximately 78.5 or 0.54 centimeters squared. I'm kind of used to the 2 decimal places convention, but hey, mileage may vary, so check with your teacher or teachers over time. So, find the area of a circle that has a diameter of 11.4 millimeters. Well, we know that area is equal to pi r squared. Okay, pi. What's the radius? Oh, it's 11.4 over 2 squared. So, pi 11.4 divided by 2, well, that's 5.7. We'll square that. 5.7 squared times pi. And, I mean, yes, you should probably state a 32.49 pi. This is exact value. But often you can just say this is exact value, and very few people will complain, actually, if you leave an exponent in there. I mean, unless it's something ridiculously simple like, oh, 2 squared. No. But if it's like 2 to the 11th power or something, people are going to be like, ah, whatever. Okay. So you state the exact value, and then you approximate. I mean, unless the question says just keep exact value, in which case, yeah, of course you don't bother with going any further. So this is approximately 102.07 millimeters squared. Let's find the area of each of these circles using 3.14 for pi. Be very careful. If you get into the habit of pressing the pi button on your calculator, you may get some of these problems wrong if you're told to use some other value for pi, like 3.14 or 3.14159 or whatever. Okay, so round to the nearest tenth. Radius equals 4.6 centimeters. Well, the area here is going to be pi r squared. So that is going to be 3.14 times r squared, 4.6 squared which leaves us with, because it said use 3.14 for pi, we didn't have to make a statement of 4.6 squared times pi. We could just substitute right in, so 4.6 squared times 3.14. This is approximately 66.4. That's the nearest tenth, and this is centimeters squared. Radius 14 meters. Area equals pi r squared. 3.14 times 14 squared. So, 14 squared times 3.14. This is approximately 615.4. Diameter equals 2.5 yards. Well, that's going to be area equals pi r squared, which is 3.14 times 2.5, so 2.5 divided by 2 for the radius. And this is squared, so 1.25 squared times 3.14. This is approximately 4.9. And what are the units? Because remember, guys, units are important. Well, this one was meters squared and this one was yards squared. Now let's say we have a diameter of 9.75 kilometers. Okay, well, this is still area equals pi r squared, which will still give us 3.14 as the question specifies, and then 9.75 divided by 2 squared. 9.75 divided by 2 squared times 3.14. So this is approximately 74.6. And this is kilometers squared. If you have a complex problem, often you just have to break it up into parts and do each of the parts themselves. And usually this will lead you to a aha moment on how to finish up the problem. If you have a complex shape, break it up into simple shapes and calculate them separately. Assuming, of course, that your problem requires that you calculate them. Otherwise, hey guys, this is art class. Draw a circle of whatever radius, and then you start doing math on how much paint you need. No. So, yeah, read questions carefully, guys. So let's say a school wants to put fake grass on a rectangular field of 200 meters by 150 meters, except for a quarter circle near one corner which has a radius of 100 meters to be set aside for a baseball field. What is the area of fake grass required? Well, we can draw ourselves a little diagram. I mean, that part is kind of there, but it's been cut out, really. So, we can draw ourselves a little sketch and then be like, fake grass, FG. Okay, what is this area? Can we calculate it directly? No, it's not practical. So we take the overall field and we subtract the part that we're not covering. Therefore, the area is equal to length times width minus 1/4 of pi r squared. Length 200, width 150 meters, minus 1/4 pi r squared, that's 100 squared. So 200 times 150 gives you, also known as 100 times 300, so 30,000 minus 1/4 of 10,000 pi, or 2,500 pi. This is the exact value in meters squared. You can bracket the whole thing if you like. So, what is the area of fake grass required? Is this number particularly useful? Like you go to a company that sells fake grass and installs fake grass and be like, I need 30,000 minus 2,500 pi square meters of fake grass. They'd be like, please get a calculator. Well, I mean, they have a calculator themselves. They probably won't turn down your business, but that's what they'll probably be thinking. Like, why didn't you do your math yourself? So, 2,500 times pi. I used the button on my calculator because it didn't specify what pi to use. Negative plus 30,000. And we end up with approximately 22,146.0. This is meters squared. Approximately. The baseball field here is actually pretty average for baseball fields. Like they don't actually get that much further from the plate to the fence than, I mean, up to 400 feet in some places, which is about 120 meters. Yeah. Suppose you have enough certificates from competitions, and suppose these are letter-sized paper, so 8.5 by 11 inch, to wallpaper your walk-in closet, which is 8.5 feet tall. 1 foot is 12 inches. Oh, hey, how convenient. So it's 12 pages tall, 11 feet wide, and 16.5 feet deep. Okay, so it's 12 pages wide. This, of course, means that you're laying all the papers on their sides. And 16.5 feet deep, with the door being a convenient 77 inches tall and 34 inches wide. By the way, this is actually slightly narrower than your average North American door, which is supposedly, according to me looking it up, about 36 inches wide. And 80 inches tall, I think it was. Oh, well, whatever. So 77 inches tall. That's an exact number of papers. How many certificates do you have? So assuming that you have exactly enough to wallpaper your walk-in closet. So the closet is 10 certificates. Tall. Remember, most certificates are printed in landscape, so this wouldn't even be turning the certificate on its side. They're just naturally wider than they are tall, usually. 10 certificates tall and 11 feet wide, 11 inches to 11 feet. That converts to 12 wide. And 16.5 feet deep is 1.5 times the width, so that's 18 deep. The door is 77 inches tall. That means if we put all the certificates that are printed in portrait, i.e. vertically, as we end up with 7 of them and 34 inches. Oh, hey, what's 8.5 by 4? Oh, it's 34 inches. How convenient. certificates, tall, and 4 wide. Now there is a problem here, as in, where is your door handle? Because your certificates, if you're papering the door with them, but are we? Like, if we had to paper the door with them, we have an issue with where we put the door handle. There wouldn't be any space for them if we paper the whole door. But it doesn't say decorating paper for all the walls and doors. It says wallpaper. The question said wallpaper. Therefore, we have to take the dimensions of the closet, calculate how much area is on the 4 walls, and then we subtract the door. Therefore, if the fit is idealized, you have ten by 12 plus 18 by 2 minus 7 by 4 equals, the 10 by this is the width and depth multiplied by the height, and then times 2 for the other 2 walls that are the same. This, of course, assumes that this is a rectangular walk-in closet. And then you subtract the door. Whoa. Wait a second. There's a problem. What is the problem? Well, I'll tell you in a sec after we calculate this. So 12 plus 18 is 30, and then times 20 gives us 600 certificates minus 7 by 4, so 28, which comes out to 572 certificates. This is rather an impressive number. If you use the correct portrait frames, I could probably paper a smaller closet with certificates, but like 11 feet wide is a bit over 3 meters, and 16.5 feet deep is like pretty deep. It's like 5 meters deep. This is a small bedroom, pretty much. So yeah, if I had the right sort of frames, I could probably cover the walls of a small walk-in closet with my certificates. But as is, like if you're just using bare papers, 572 is a bit ridiculous. But we also have another problem, guys. Notice that the door is 77 inches tall. And notice that the other certificates we used to cover the walls were laid out horizontally, like this, in landscape, whereas the door was vertical. We have a spacing problem. So, this question, like most other math questions, is obviously highly idealized. So the answer is, in fact, this many certificates. Note this would would not actually be possible. Be possible. As well, 8.5 feet by 12, 102 minus 77 is 25. So that means you have like 3 rows of certificates where you have to cut a little bit off the bottom, half an inch. The space above door or to sides of door, no matter how you place this thing, do not allow whole certificates. Whole certificates. Yeah, this is a bit of a problem, huh? Well, at least it's still saner than the person who goes to, supposedly goes and buys, I don't know, a couple thousand bananas at once and is not a grocer. Like, he doesn't sell bananas. Or somebody who eats like 300 candies at a time. But hey, that's math class for you. It doesn't have to make sense. Well, I mean, it doesn't have to make sense in practice. The numbers all have to work together. Area of complex figures. It's made of triangles, quadrilaterals, semicircles, other two-dimensional figures, added or subtracted. So to find the area, separate into figures that you know how to find, and then add or subtract the areas. So find the area of the figure in square feet. Well, in this case, we have a rectangle. Area equals length times width plus 1/2 height times base 1 plus base 2. Length is 12 feet, width is 8 feet, plus 1/2 height is 4 feet. And then base 1 plus base 2 is 12 feet plus 4 feet. So, looking at 96 plus 2 times 16, which is 32. So this is 128 square feet, or feet squared. Okay, let's do some exercises. Find the area of each figure and round to the nearest tenth if necessary. Well, here we can go with 2 trapezoids. Or we can go with a rectangle minus a triangle. I'm going to go with the rectangle minus the triangle. Okay, so area is equal to length times width minus 1/2 base times height. Length is 13, width is 6, minus 1/2. Base is 13. Height is 6 minus 4, which is 2 centimeters here. So we're going to be looking at 13 times 6 minus 13. So 78 minus 13, which is of course 65, or 13 times 5. What are the units? Oh, it's centimeters squared. Okay, what about this diagram? Well, it's a rectangle minus 2 times 1/2 pi r squared. So length is, we know that this part is going to be 2.5 inches and this part is also 2.5 inches because they are half the diameter each. Therefore, we're looking at 9 inches times 5 inches minus pi r squared, pi, and then radius is 2.5 squared. So 5 times 9 is 45, and then minus 2.5 squared times pi. Isn't that just 6.25 times pi? 25 pi. Okay. Times pi, well, negative pi plus 45, and we would get approximately 25.4 inches squared. Yeah, I'm just go with the nearest tenth because it says round to the nearest tenth if necessary. Okay. What about this figure? Well, let's start cutting it up. Oh, hey, we got a trapezoid and we got a semicircle. Area equals 1/2 height times base 1 plus base 2 plus 1/2 pi r squared. So that's 1/2 times height. 11 millimeters is the radius. So twice that is going to be 22 millimeters. And base 1 plus base 2, that's 18 plus 38. Plus 1/2 pi. R squared is 11 squared. So 18 plus average of 18 and 38 is just going to be 28 times 22 is going to be 616 plus 121 over 2 pi. Yeah, this doesn't strike me as a particularly useful number. Therefore, we got to approximate times pi. Approximately 806.1 millimeters squared. Now, for three-dimensional figures, they come in a few flavors as far as we're concerned. Like, we're only dealing with regular geometric figures here. Not to be confused with regular polygons where all the angles and sides are equal. Regular means like conventional, the things that we often see. We're not dealing with, say, a blob, like a rock. Well, most rocks. So a prism has at least 3 rectangular lateral faces. The top and bottom bases are parallel in a prism. The shape of the base tells you the name of the prism, like say a triangular prism, or a rectangular prism, or a quadrilateral prism, or a pentagonal prism, or whatever. A pyramid has at least 3 triangular lateral faces, and it has one base shaped like any polygon, so any closed shape. The shape of the base tells you the name of the pyramid. It can be, say, a square-based pyramid, a rectangular-based pyramid, any other quadrilateral, like, say, a rhombus or parallelogram-based pyramid. It doesn't matter. And then there's like triangular pyramids, pentagonal pyramids, and so on. The point of a pyramid is basically you take a shape, any closed shape that has straight sides, so any polygon, you draw a line from each vertex up to a common point, and you fill in those faces that you've just made, the triangular shapes that you just made, and you have a pyramid. A cone has only one base, and the base is a circle, and there is one vertex, and there are no straight edges. The one edge that you can find on a cone is a circle, so the circumference of the base. Cylinders, they only have two bases. The bases are circles, and there are no vertices and no straight edges. Like say this is a cylinder. A sphere has all the points being the same distance from the center. It's a circle but in 3 dimensions. It's the set of all points that are the same distance from that central point. There are no faces or bases, and there are no vertices or edges. Now for each of these figures, name the shape of the bases, then classify each figure. Well, this we see that you have a bunch of parallel edges, each with a rectangular face. So this is a prism. What type of prism is it? It is a triangular prism. Triangular prism. Okay, what's this? This has two faces that are parallel. They are both circles. This is a cylinder. Alright, what are the shapes of the bases in these? Well, this you can say that the ends are the bases. You can say, well, really any pair of sides that oppose each other are the bases. But the shapes of the bases are still rectangles. Rectangular bases. And this is therefore a rectangular prism. Rectangular prism. Now what about this thing? It has circular bases and it is a cylinder. What about this shape? Well, it has a triangular base and it's a triangular pyramid. Base and triangular pyramid. 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 How about this one? Well, we see that there are two parallel faces. So these parallel triangular faces are the bases. Bases. Triangles. And this is a triangular prism. Triangular prism. Now, what about this shape? Oh, it has one circular face and then a curved face that goes up to a point. This is a cone. And the base is a circle. Base, circle. Now, this last shape here, well, any pair of opposing faces could be the bases. The bases are squares. Squares. call this shape a cube. Now let's say we gotta draw three-dimensional figures. Okay, so we got a solid using the top, side, and front views shown below. From the top, it just looks like 3 blocks. From the side, it looks like this shape, and from the front, it looks like, well, 3 blocks. Okay, then. That suggests that if we use isometric paper, as is usual, we're going to end up with a shape that looks something like this. Isometric paper, by the way, has a grid of dots that are the same distance from each other, i.e. any 3 dots next to each other will make an equilateral triangle. This will, of course, depend on conventions for which side represents the front. Like in some places, the front is you look at the paper this way. The paper looks like a grid of dots, like this, by the way. So you can just draw lines in whatever way. They're all equidistant from each other, the neighboring points. Top, this side was the front in this particular version. Front. And this side was, well, the side. Yeah, this is a solid that you get from these views. Let's say we got to draw a top, side, and front view of this solid. Well, from the top, it's a hexagon. Now we can't say whether it's regular or not from the diagram shown, so yeah, top is going to be something like this. You should use a ruler if whatever you're drawing on possibly permits the use of a ruler, by the way. And the side, well, this is side, top, front is from, well, here. Okay, the side is going to look like this. Yeah, this should be evenly divided, and front is going to look something like this. Depending on how regular this hexagon is supposed to be. Alright, draw the solid whose top, side, and front views are shown. Usually for this type of problem, you'll use isometric dot paper. We don't have that available right here, so we'll just have to make do. Don't worry, guys. At least making do is less terrifying than designing by committee. There is a saying among engineers, none of us alone is as stupid as all of us put together. I mean, isometric dot paper wise, these 2 points should actually join together. But for the purposes of this diagram, I'm just going to draw it like this so that we can see what's happening here. Alright? Because otherwise, isometric dot paper could look a little bit awkward on showing that thing out there. The bite taking out the side. Well, this means the front would have to be this side, front, top, and this would be the side. Volume of prisms. The volume of a three-dimensional figure is the amount of space that it occupies. It's measured in cubic units like cubic centimeters or cubic inches or whatever. A rectangular prism is a three-dimensional figure with two parallel and congruent sides or bases that are rectangles, and the rest of the sides are also rectangles going up, connecting these bases. To find the volume of any prism, multiply the area of the base times the height. Let's find the volume of a rectangular prism with length 6 centimeters, width 9 centimeters, and height 5 centimeters. So for any prism, the volume is base times height, but for a rectangular prism, the base is capital, instead of capital B, we can put length times width, and then times height. So that's 6 centimeters by 9 centimeters by 5 centimeters. So 5 times 6 is 30, times 9 is 270, and this is in cubic centimeters. Let's do some exercises. Find the volume of each rectangular prism. Round to the nearest tenth if necessary. It won't be because here we're just multiplying whole numbers. So, this is volume equals length times width times height equals 4 times 6 times 7. So, 6 times 7 is 42 times 4, that's 168 meters cubed. Okay, 9 inches by 10 inches by 12 inches. Well, volume equals length times width times height. So 9 by 10 by 12. So 9 by 12 is 90 plus 18 or 108 times 10. 1080 inches cubed. Let's say we want to find a cylinder's volume. Well, a cylinder is also base. You can think of this volume as in layers of, say, unit blocks or something if you like. So you get one layer, that's 1 unit tall. And how many of those layers do you need to go up the full height h? You need h layers. Therefore, it's still base times height. And in this case, base is pi r squared because the base is a circle. Let's say we have a radius of 5 inches and height 9 inches. Use 3.14 for pi and round to the nearest tenth. Okay then, volume equals base times height equals pi r squared times height equals 3.14 times r squared. So radius is 5 squared times height, which is 9. So 5 squared times 9 times 3.14 is 706.5. And this is in inches cubed. Why is it in inches cubed? Well, radius was in inches, and we squared that, so we ended up with square inches, and multiplied by height in inches, which was inches squared times inches. That's inches to the third power, cubed. Turns out we didn't actually need to round. Wonderful. Exercises. Find the volume of each cylinder. Use 3.14 for pi and round to the nearest tenth. Diameter 50 millimeters. Length 365 millimeters. Okay. Volume equals pi r squared h. That means 3.14 times 25 squared times h, which is 365. Now the way that this says length suggests that this is a cylinder that's lying on its side. Now 3.14, 25 squared times 3.14 times 365. Round to the nearest tenth. Well, it turns out I didn't need to round. This is equal to 716,312.5 millimeters cubed. I think I overestimated the base length, the base diameter of the cartridge for the 40 millimeter by 365 millimeter. Diameter 15 inches, length 630 inches. Wait a second. Isn't this the bored out volume, approximately, of a 15-inch 42? Which equipped the Royal Navy 15-inch armed battleships from the First World War into the Second, and until after the Second World War. Yeah, that's exactly what it is. But anyway, so diameter 15 inches, length 630 inches. This is pi r squared h. Therefore, it's 3.14 is what we're using for pi. And then r is 7.5 inches squared times 630 inches. So, 3.14 times 7.5 squared times 630 leaves us with approximately 111273.8. And this is in inches to the third power. Let's say the next one we're looking at has a radius, the next cylinder, has a radius of 4.5 millimeters and height 19 millimeters. So the volume is equal to pi r squared h. And that's going to be, it's 3.14 is what we're using for pi. And then r, I'm just so used to writing exact values. Oh well. Squared, and then h, 19. Actually, depending on region, even if you're told to use an approximate value for pi, some places still favor substituting pi in as a last step. So you should make sure you know what your teachers look for. That's slightly important because they mark your stuff. Times 3.14 times 19, approximately 1208.1 millimeters cubed. All right. Well, that's it for this chapter, which was on areas and volumes. So, see you another time.